Okay, so in this video we're going to be talking about what a derivative is. I think it's like a really important part of calculus. You probably heard of it before, but in your class you don't really spend that much time talking about the conceptual definition. You just, spend a day or two on it and then move on to math. So I'm going to try to really help you understand what a derivative is conceptually and then go into the math and derive the actual, technical definition of the derivative. Okay? So you don't need to know any calculus for this. All you need to know is some algebra, some geometry, and you need to know what limits are and how they work. So if you know all those things and you want to learn what a derivative is, let's get started. So the first thing I'm going to do is I'm going to define the tangent line. You've probably heard of a tangent line in geometry class, probably with circles. A tangent line, you might have drawn tangent lines to circles and used equations with them. So a tangent line is a line that just barely touches the graph at exactly one point, like that. It barely touches this line here, for example. This touches the circle at two distinct points, but my tangent line, it touches the circle at exactly one point. It's a tangent line. Okay, now that we got that out of the way, I want to show you that that definition of a tangent line, it doesn't only apply to circles and other shapes. You can also use it with graphs. So with this graph, y equals x squared, I can draw my tangent line as well. So maybe I want to draw a tangent line at this point here at x equals 2. So if I draw a tangent line, I'm going to draw a line that barely touches the graph at x equals 2, and it's going to look, I don't know, maybe something like this, right? It barely goes there, it touches it, and then it moves away again, alright? And then I'm just going to tell you straight up now, a derivative is the slope of the tangent line. So at my point x equals 2, the derivative of this graph of y equals x squared is the slope of the tangent line at x equals 2. Okay? So now that we've got the actual definition of the derivative out of the way, which is, again, the slope of the tangent line at a point, let's try to figure out how we can find that slope. Remember how the slope form is y2 minus y1 over x2 minus x1? Well, we can't really figure out the slope of this tangent line in that way because we only have one point on the graph here, right? We can't really plug in the same point because then we'll get 0 over 0. It's not going to work, right? So how do we figure out the slope of the tangent line using only one point? Well, here's what we're going to do, okay? We're going to first start by approximating the slope. So let's say I take this point here, and I take this point here, and then I draw another line. I'm going to say, well, this line is like an approximation of the tangent slope, or the approximation of the tangent line. It's like not exactly this slope, but it's like, I'm trying to draw the slope. And it's obviously really, really bad approximation, but it is an approximation nonetheless, right? But if I wanted to calculate the slope of this line, now I can do this because I have my x1 comma y1 and my x2 comma y2. So I could, find this is 0 comma 0, this is 2 comma 4, so I could plug that into here and I could find my slope of this blue line. Well, that's great and all, but how do I find the slope of the red line? I don't really care about the slope of the blue line because that's like just a terrible approximation. It's not the actual slope, right? So the way we're going to do that is I'm going to define a new variable here. The variable is going to be h, and the variable h is this horizontal distance between the x values of the first point and the second point. So if this is this first point here, and it's at 0, and the second point is at 2, this horizontal distance here, which is 2, I'm going to call that h. Okay? That's going to be an important variable in our math part coming up in a sec. So now that I've defined my variable h, I can start getting into the math behind where the technical definition comes from. Alright? So first of all, y is just f of x, right? So I can replace my y's, and I'll just do this. I can replace my y's with f of x's. So f of x2 minus f of x1, right? This is my this is x1 comma f of x1. This is x2 comma f of x2. And don't forget this distance h here. That's still going to be important. All right. So if this is my x1 and this is my x2, I can write that x2 equals x1 plus h. So for example, if my first point was here and this was my tangent, if this was my slope, my h would be this distance. And I think in the second example it's more clear that if if this distance is my x1 and then this distance is my x1, this is my h, and this total distance is my x2, it's pretty clear that x1 plus h equals x2, right? So now that I have that x2 is x1 plus h, I can take this and plug it into here and see what happens. So instead of x2 here, I'll write x1 plus h, which will give me f of x1 plus h minus f of x1 over, and then again, I have an x2 here. I'll replace that with an x1 plus h minus x1. And then a neat thing happens. This x1 here cancels with this x1 here. So these two cancel each other, and we're just left with the h on the bottom. Right? Let me rewrite that. F of x1. Actually, hang on. Let me just move that over a bit. I'll say f of x1 plus h minus f of x1, and then the x1s are gone here, so I'm just left with h in the bottom. And let's just remember what this is. This is just this form here to find the slope of any line in general, and I've rewritten this in terms of h, where h is the distance between the two x coordinates. Right? This is just the slope formula for finding the slope between two separate points, just been manipulated into this h form. Okay? And then now let's think about what happens when I notice that at this first blue line, h is 2, right? At the second blue line, h is smaller. So as my first point moved up here along the graph, my h got smaller. As I move the first point closer and closer up the graph, if I move my first point even closer, if I move my first point up here, and I drew this line, I don't know if you can even see that, my h is really, really small, right? So as the first point and the second point get closer and closer together, the distance h between them becomes 0. I think that's pretty clear, like in the graph. As those 2 points get, closer and closer together, the distance between them becomes 0. And h is the distance between them, so h becomes 0 as the 2 points get closer and closer together. Alright? So since this is the slope of the line, of the blue line, I can take the limit as h approaches 0, and this limit is going to give me the slope of this tangent line. Because I'm saying, okay, what happens to the slope as the distance between the lines, the distance between the coordinates, h, approaches 0. So as x1 and x2 become the same point as they get closer and closer together, what happens to the slope? And I'm just going to do one more thing here. Since there's only one x, there's not an x1 and x2, I'll just remove the 1 and I'll call this an x. So now we have f of x plus h minus f of x over h, the limit as h approaches 0, and this limit here, this is basically the form for the slope of the tangent line. Okay? I'm just gonna box that in. If you look in like a textbook or whatever, you'll probably find this as the technical definition for the derivative, the limit as h approaches 0 of f of x plus h minus f of x over h. And just note that this is the formula for the slope between 2 points, and we're taking the limit as the distance approaches 0. As you do that, the 2 points become the same, so this form is going to be useful for finding the slope of the tangent line. Right? You might also see it written like this: the limit as x approaches a of f of x minus f of a over x minus a. And where this comes from is if you have, one point A and another point X, you're seeing what happens as X approaches A, as one of the points approaches the other point. And this is the same thing. We're trying to find out what happens as the 2 points get closer and closer together, as the distance between them gets less and less. So these are the two forms you'll see for like the limit definition of the derivative. And just in case you're curious, if you're like, I really want to find the slope of this tangent line at x equals 2, we've been talking about it for so long, I want to actually find out what it is. Well, I'm going to show you how to do that, right? We're going to use this top form here. So the limit as h approaches 0 of f of x plus h minus f of x over h. I'm going to show you how to actually apply this formula with like a concrete example. Okay? In our graph, f of x is x squared, right? So I can take the limit as h approaches 0. Instead of saying f of x plus h, if I have an x plus h here, this will be x plus h squared. So I'll have an x plus h squared here minus f of x. Well, f of x is just x squared, so it's just going to be x squared, and then over h. And then if I expand this, I'll get the limit as h approaches 0. And I get that it's getting more and more mathy as the video goes by, but like once we're done with the conceptual part, there is really a lot of math. There's no getting around it. This is going to be x squared plus 2xh plus h squared minus x squared over h, and then this x squared and this x squared, they cancel with each other, and then we get the limit as h approaches 0 of 2xh plus h squared over h. And then notice that we have an h here, we have an h here, and an h here, so I can cancel this, I can cancel this, and this will become a plain h. This is the limit as h approaches 0 of 2x plus h. And as h approaches 0, this term is going to go to 0, and then that's just equal to 2x. Okay? So what does this really mean now? We did all this fancy math using our limit definition. What does this all mean? Well, it means that the slope of the tangent line at any point is 2x. So going back to our original thing here, let's erase all of these lines, and let's redraw our tangent line at x equals 2, like that. This tangent line, remember the whole point is to find the slope of this tangent line. Well, we did all this math, and we found out that the slope of the line is 2x. And since we're at x equals 2, the slope of this line is 2x. Is going to be, so the slope is 2x. And since we're at x equals 2, I shouldn't have done that in white. X equals 2, so the slope is 2 times 2, which is 4. So the derivative of our x squared graph is 2x, and then the derivative at x equals 2 is 4. And this makes sense because if you took another point, like say you took x equals 0, the tangent line is going to be a flat line here. Right? It's just going to be right along the axis, right, like that. Right? It's clear that this tangent line at x equals 0, it has a slope of 0. And if we plug that into our 2x equation, we'd have 2 times 0, which is 0. And the slope of this line is 0. You can use this 2x thing at anywhere along this graph. You will get an answer. Like if you wanted to find the slope of this curve at 23, You take 23 times 2 is 46. So the slope at x equals 23 would be 46. Okay? So I hope you found this, combination of conceptual plus a bit more mathematical near the end. And I hope you for hopefully more clearly understand what a derivative is. It's the slope of a tangent line, and you also understand like the math behind it and where all that comes from. Okay, so hope you found this helpful, and I will see you in another video. Goodbye.